Hi, my name is Sharon Silverman from the Global Clinical Marketing team. I'm joining Jay Washatek here to walk you through performing cardiac strain on your LOGIQ system.
Hello, my name is Jay Washatek, and I'm the Cardiovascular Ultrasound Education Lead for GE Healthcare, and we are here today to talk about strain. All right, so let's get started with the fundamentals of strain. And what we're going to do with this presentation is give you a very intuitive and technical understanding of what strain is. And I say intuitive because if you have an intuitive understanding of what strain is, you can apply it to pretty much any situation that you need to. We want to talk about how we calculate strain. How does the system come up with these strain numbers, i.e. speckle tracking? And then we're also going to go over what constitutes a normal and an abnormal strain curve. So the first thing we need to do is actually define what strain is. And as it turns out, there are a lot of definitions of strain. If you go to Wikipedia and type in strain, you will see that you get a lot of definitions. Fortunately for us, there's only one definition that we need to worry about, and here it is. This definition is that strain is a deformation of a body or structure as a result of an applied force. So here's the thing. When the engineers first came to me with this definition many years ago, I looked at them and said, can I have a definition for this definition? So we are going to define exactly what this means.
So the way we're going to get a definition for our definition is by transforming these terms that we're going to be using for strain from what I call nerdese into plain English. And nerdese is basically the language we're going to use when we're talking to engineers or cardiologists or fellow sonographers. And we're going to translate that into something that just makes sense in plain English. So the first term we're going to define is deformation, because we've already seen that strain is the deformation of a body or structure as the result of an applied force. What does that mean in plain English? In plain English, it simply means that something changed its shape. And that's pretty much all it means. It's that simple. So here are some other terms that we need to look at when we're talking about strain in the heart. So we've already said that strain is the deformation of an object, meaning that something changed its shape. But other terms that we need to be aware of is positive and negative. In other words, when we talk about strain, we give it a sign. So what does positive strain mean? It simply means that something changed its shape and it got bigger. What does negative strain mean? Basically, something changed its shape and it got smaller. The other thing that we do is define a direction for that strain. So in cardiology, here are three types of strain, the three most common types of strain that we talk about. First is longitudinal. So when we talk about longitudinal strain, we're talking about something getting taller or shorter. Radial strain we can think of as something got thicker or thinner. And circumferential strain we can think of as something getting fatter or skinnier. So in other words, if I were to say in nerdese, something experienced negative 20% longitudinal strain, in plain English what I'm saying is that it got 20% shorter. If I talk about something experienced positive 35% radial strain, basically what I'm saying is that it got 35% thicker.
So one of the best ways to illustrate what strain is and how to apply it to the heart is to use a toy called the Hoberman sphere. So a very good way to get a very good intuitive understanding of exactly what strain is to use this little thing here. It's a toy called a Hoberman sphere. And the way we're going to use this is we're going to look at this Hoberman sphere as it contracts down and expands back out. And we're going to describe, using the nerdese that we just learned, we're going to describe that motion for the Hoberman sphere. So the first thing that we want to look at is the distance between this finger here I have on the Hoberman sphere and this finger here. And you see as we contract down with the Hoberman sphere gets shorter, right? The distance between those two fingers gets smaller. And as it expands back out, it gets taller. So how would we describe that in nerdese? basically we're going to say as it contracts down, it's experiencing negative longitudinal strain. And as it contracts back out, it's experiencing positive longitudinal strain. Now, the other thing we want to look at is the thickness of the wall of the Hoberman sphere, and that's represented here by the distance between my forefinger and my thumb here. Okay, so as I contract down, you can see the distance increases, i.e. the thickness of the wall of the Hoberman sphere increases as I contract down, and it decreases as I expand back out. How am I going to explain that in nerdese? I'm going to say that it's experiencing positive radial strain as I contract down, and then negative radial strain as I expand back out. Now, the interesting thing is that during the same motion, while the Hoberman sphere is contracting down, it's experiencing negative longitudinal strain, while at the same time experiencing positive radial strain. Now, the other direction that we want to look at is the circumferential direction. And this is represented by the kind of yellowish-orange line right there in the middle of the sphere. So what happens to the circumference of the sphere as we contract down? It gets smaller. So how are we going to describe that? We're going to say it's experiencing negative circumferential strain as it contracts down, and positive circumferential strain as it expands back out. So this is going to be no surprise to anyone. As it turns out, the heart changes its shape due to a force. Therefore, we can actually talk about strain within the heart. And as it turns out, it is a really good way to quantify LV function. And we'll go over that in just a little while. But just keep the concept in mind that this is a way that we can quantify LV function both segmentally and globally. So based on what we've already learned about strain, looking at these different mock-ups of the heart, and we're looking at the different ways that the heart contracts. For this first image right here, what kind of strain would you guess that we're looking at here? Since we're looking at the wall thickening, hopefully you guessed that was radial strain. Now in this image, we're looking at the base of the heart moving towards the apex of the heart. In other words, the heart is getting shorter and taller. Hopefully you guessed longitudinal there. And now we're looking at the circumference of the heart, looking at that donut when you look at the short axis of the heart, getting bigger and smaller during systole. So that would be looking in the circumferential direction. So let's do one more practice, and then we'll get on to looking at the actual curves that are produced from this. So in this instance, we are looking at 2 points in the left ventricle, in the septum here. At end diastole, these 2 points are 10 millimeters apart. At end systole, these 2 points are 8 millimeters apart. How would I say that in nerdese if I wanted to describe this in strain terms? Well, the first thing, again, is we want to assign it a sign. We went from 10 to 8, which means it got smaller, so we're going to assign it a negative. We started with 10, we lost 2, that's a 20% change. And we're looking at this ventricle getting shorter during systole, so we're looking at longitudinal strain. So the way we would describe what happened here is negative 20% longitudinal strain. And by the way, I'll let you know that of the 3 types of strain that we talked about, longitudinal, circumferential, and radial strain, those are the 3 that are most talked about in cardiac right now. Of those 3, longitudinal is the one that has been the most researched. It's the one that is validated, and it's the one that people are using clinically quite often. So now let's look at the curves. And by the way, when you do a strain study, you get one of these curves for each segment of the heart. So we're just going to tease out a couple of curves and go over what makes a curve normal as opposed to abnormal. And we're looking at longitudinal strain here. And let's look at this black curve first. The first thing I want you to notice is that we have an aortic valve closure line here. Very important when you're looking at strain curves to have this aortic valve closure line. So on the left side of that aortic valve closure line is systole. On the right side is diastole. So the first thing that we want to look at when we're trying to decide, is this curve normal, is we want to think about longitudinal strain and think about how the heart contracts, i.e. the heart gets shorter during systole. So we're expecting longitudinal strain to be negative. And when we look at this curve, during systole, it's going in a negative direction. That's one check mark for normal. The other thing we want to look at is, where does this curve hit its peak compared to where the aortic valve closure line is? And we see that this curve hits its peak right at aortic valve closure. That's our second check mark for normal for this curve. The third thing we want to look at is the magnitude of the strain. And right here we have a negative 20. And in general terms, for right now, longitudinal strain, normal for longitudinal strain, is negative 18% or below. And by below, I mean negative 19, negative 20, negative 21, going down that way. That's going to be normal. We see here that this curve's magnitude is about negative 20. That's our third check mark for normal. So now let's look at this red curve and see what's going on. You see here during systole, it's longitudinal. We're expecting a negative value, and it's actually headed positive during the first, I guess, 3/4 of systole there. So what's going on there? The ventricle, the segment that line is representing, is actually getting taller during systole when it should be getting shorter, right? So this correlates with dyskinesis here. But you notice that towards the end of systole, this line actually does start to experience negative longitudinal strain, but it doesn't hit its peak until well after the aortic valve closure. That's another indication that this is abnormal. So first indication, we're getting positive values when we're expecting negative values. Second indication, our peak hits well after that aortic valve closes. And if you think about it, in terms of energy, this segment is expending a lot of energy trying to contract against a closed aortic valve. That's wasted energy. So if you want to think of it as inefficient contraction, that's a good way to think about it. The third thing that we want to look at is the magnitude. And we see here the magnitude is negative 5%. Again, that is well above the negative 18 for our normal. So that's the third indication that we have an abnormal curve here. Now, there's actually a fourth thing that we want to look at when we're trying to decide if a set of curves is normal. So now we're looking at a set of longitudinal strain curves. And what we want to look for is how synchronously they contract together, how well these lines follow each other. And this is an example of good synchrony. All of these lines are following each other very nicely. So we're going to say that that's good synchrony there. However, when we look at this graph, we can see that this set of curves comes down like this, and many of these graphs don't hit their peak till well after the aortic valve closes, right? But now we have another set of curves that are coming down like this, going up, and you can see where these curves actually cross each other in systole, creating an X here. That is an indication of dyssynchrony. So in other words, if you think about the heart, a very efficient way to pump is if all those walls are coming in together at the same time to pump the blood out of that aorta. What happens if one wall is coming in later than other walls? It's more like it's churning the blood as opposed to pumping it. Not an efficient way to pump the blood out of the heart. So this would be another indication of abnormal strain curves. So there are a couple ways that you can calculate strain. And the reason I bring up tissue Doppler strain, it was the first way of doing strain. It is possible to do tissue Doppler strain still. And the reason that I really like to bring it up is because when you're reading articles about strain, you will see many articles where many researchers are still using tissue Doppler strain, even though we have a better way of doing it now in the clinic. But just to get you familiar with that when you see that in those articles. So we can use Doppler to calculate strain. And here's the principle behind it without getting into any complicated calculations or anything like that. If you think about it, This, during contraction, the base of the heart here is moving towards the apex during systole. We also know that the base of the heart moves more and it moves faster towards the apex than the midsections of the ventricle, and the midsections move more and faster than the apical section. So in a normal heart, we've got these 2 points. We've got the distance between those 2 points. During systole, both points are moving towards the apex. However, in a normal heart, this point is going to be moving faster than that point. So just think about it intuitively as both of these points are moving this way. This one's moving faster than that one. What happens to the distance between those 2 points? It shrinks. Seems like we should be able to plug that into a formula and calculate strain, right? And as it turns out, you can. So this is tissue Doppler-based strain. It was the first type of strain that came out. There was a problem with tissue Doppler-based strain, and not to diss it because we were very glad to have it when it first came out, but it is angle dependent, as is all of our Doppler measurements are angle dependent. So that was a major drawback when tissue Doppler came out. But once again, you will see articles and researchers who still use tissue Doppler strain. So it's good to be familiar with it and know what its limitations are. So the solution to that was called speckle tracking strain. This is the strain that is being used clinically. This is the strain that is validated for clinical use. So what is speckle tracking strain? Speckle tracking itself is just a method used to calculate strain. So how does it do it? As you know, any ultrasound image is basically just a collection of speckles put together to look like a certain organ, in this case, the heart, and in this case, the septal wall of the heart. Well, we can break up those speckles into speckle packets and come up with patterns for each one of these speckle packets. And these patterns are so unique, it's like a thumbprint. The system can actually trace that packet through systole as it moves through systole. So if we have the ability to do that, it's not hard to imagine that we could actually introduce a second point, measure the distance between those 2 points in diastole, and then again measure the difference between those 2 points in systole, and calculate the strain directly. So a major advantage to speckle tracking strain is that we don't have to put these numbers through any calculations. We're directly measuring the strain using this speckle tracking technology. And it got rid of our angle dependence. And so the only limitation, or I will say the only major limitation of speckle tracking strain, is that it is 2D image quality dependent. But as it turns out, everything we do in ultrasound is image quality dependent, right? So we're at a very good point with speckle tracking strain. So on your systems, your strain package is called cardiac strain. When you go into your cardiac strain package, you are using speckle tracking strain to calculate longitudinal strain for each one of the segments in the heart, and also a global number. And we'll go over those in a little while in a future video. So